All right, class, sorry about the interruption, but apparently the tablet can only get so full and then it stops recording. So we're having to pick up with a second video here. And we left off looking at the point, the position that is 0.4 meters above the bottom, okay? And here we go. We said there had to be 3.9 joules of gravitational potential energy, 4 joules of elastic potential energy. Subtract those from 9 and you get kinetic energy is 1.1 joules. Now, let's take a look at the top point. At the top point, it's 0.6 meters above, not 0.6 meters. Oh, I think I wrote that down instead of what I was supposed to. It's stretched down 6.6 centimeters, but it's only 0.4 centimeters above the bottom because we've got 0, 0.2, 0.4. All right, so I do need to change that, don't I? Let me do that real quick. All right. In fact, come to think of it, that's incorrect also. I didn't, these are supposed to be by height. 0 height, 0.2 meters, 0.4 meters. Okay, I didn't notice that. All right, well, I did it again. There we go. We'll just call it quits now. All right, so at the top point, we know that it stops and changes direction. So the kinetic energy would have to be 0 at that point. But it's at a height of 0.4 meters above the bottom. So we're going to use MGH. Well, you can, and you get 7.8 joules. We also know that it's compressed by 0.2 meters from its unstrained length. Unstrained length is 0.4 meters. So actually it goes back up to 0.4. That's what the problem is. It goes back up to 0.4. Nope, here it is. I'm supposed to be, let me cover that. All right, so it goes from 0.4, which is unstrained, to right here, okay? So now we have 0.2 meters of compression. So the stretch is only 0.2 from its unstrained length, all right? So now we say 1/2 kx squared, and we get 1.2 joules. And since the kinetic energy is 0, if we say the 9 joules of mechanical minus the 1.2, we get 7.8 for the gravitational potential. And you could also use MGH and see that it is the same value. All right. Now we're going to talk about pendulums briefly. There's not as much to pendulums, so let's take a quick look. When you have a simple pendulum consists of a string and a bob, which a mass that's placed on the end. It's called a bob, B-O-B. And you pull it back and release it, and it exhibits simple harmonic motion. It goes through the oscillations in the same time period over and over. Now, I would suggest at this point that you pause the video and copy this down and then listen as we go through it after you've copied it. All right, so we have a string of length L with a mass on the end. When it's at equilibrium position and at rest, not moving, at rest, the tension and the gravity would balance. However, unlike a mass on a spring, an interesting thing happens with a pendulum bob when it's moving through equilibrium, not at rest, moving through equilibrium. A pendulum swings in a circular arc. That means you have to have a centripetal force, which always points towards the center of the circle. If the mass is moving through the center point, the equilibrium position, there must be an upward net force pointing to the center of suspension. That would be the center of the circle it would travel in if it went all the way around. So in order to have a centripetal force pointing towards the center, When it's moving through this position, the tension would have to be greater than the gravity at this point. So when it's at rest at equilibrium, T does equal mg. But when it's moving through the equilibrium point, at that point, T has to be greater than mg so that you do have an upward centripetal force. Okay, now, what actually causes the oscillations? How can we start an oscillation? Well, you pull the bob back through an angle theta, and at that angle, you're going to release it from rest. When you release it, at that instant, there are only two forces acting on the bob: the tension in the string pointing back along the string and gravity pulling straight down. Now, notice that neither of these two vectors are perpendicular to each other, nor are they parallel to each other. That makes life a little complicated. So what we do is we use our little trick. We take the weight itself and we break it down into two perpendicular pieces, one of which is at the same angle as the angle of release, okay? And if you do it that way, two perpendicular components such that you get two similar triangles here, then this component is balancing the tension, and this component is the one acting as the net force to make it accelerate back and forth. In fact, if we were to take this half of the diagram and flip it to the other side, this component would be pointing towards the center that way. So that means it makes the mass accelerate towards the center, but then on the other side, when it points the other way, it makes it decelerate to a stop and then accelerate back towards the center. Then it changes direction on this side to that again, and it decelerates to a stop and accelerates towards the center. That's what happens the entire time. You accelerate towards the center, decelerate to a stop, accelerate towards the center, decelerate to a stop, over and over and over. Okay? All right, so that takes care of the dynamics. Now, a couple of things we do need to know. And first, that is that the velocity is a maximum at its lowest point, and it's a minimum at the amplitudes. Now, that should make sense. It's going to go the fastest right here at the bottom, where it's accelerated to and before it starts decelerating. It's going to stop at the amplitudes, and of course your velocity can't get any smaller than 0. So maximum at equilibrium, minimum at amplitudes, just like it is for a mass on a spring. Now, also, the pendulum depends, the period T depends only on two things: the length of the pendulum and the acceleration due to gravity where you are. I will leave you to watch the videos to learn about that. In fact, there's an important question about this one on the video, so make sure you, I believe that's on the Friday assignment, so make sure you watch that. Some useful equations for pendulums. Now, we know that for masses on springs, we said that the angular frequency, which is what we also call angular velocity, is 2 pi divided by the period, the radians over the seconds, radians per second. But since period is the reciprocal of frequency, we can say 2 pi f. So these are the two ways you can write angular frequency. They work for a mass on a spring, but they also work for a pendulum, okay? In fact, for a pendulum, the angular frequency is also equivalent to g over the square root of g over L. Just like for a mass on a spring, omega was equivalent to the square root of k over m. Okay? Now, if we take either ratio and we put it in right here and then solve for t, we saw that for a spring, the period of a spring was 2 pi divided by the square root of k over m, but we don't want that ratio there, so we multiplied the 2 pi by the reciprocal of that ratio, m over k. That gave us a nice little formula for the period of a spring based on the mass on the spring and the K constant of the spring. We can do the same thing for a pendulum. If this is the angular frequency and we want to solve for T, then stick this right here, do numerator-denominator switch, you get 2 pi over the square root of G over L, but we don't want that ratio in the denominator, so we multiply the 2 pi, we multiply the 2 pi by the reciprocal of that ratio, so we get L over G. So we have one for each. We have the spring period and a pendulum period right there. Okay? All right, I'll leave it to you this week to watch the videos. They're pretty interesting. I like them. And to learn about the relationship between simple harmonic motion and uniform circular motion and the energies involved. In fact, I think the last page, is there a last page? Oh, yes, there is. Let's just go ahead and look at it real quick. Oh, yes, this is a very important piece of information right here. You'll notice that we said when we pull a pendulum bob back to release it, we pull it back an angle theta, an angular displacement. All right, there is a little problem with that. If you pull the bob back more than 15 degrees of angular displacement from equilibrium, you get an interesting effect called damping. For example, if I were to pull the pendulum bob back 45 degrees and release it, almost immediately I will see that there is a rapid decrease in the amplitude and therefore the period until the bob is within 15 degrees oscillation of the equilibrium point. This interesting phenomenon where it does that is called damping, not dampening. I'm not getting it wet. Damping, okay? It's just a rapid decrease in the amplitude of a mass undergoing simple harmonic motion. Actually, springs exhibit this to a slight degree also, but definitely pendulums. So what we do is we assume that ideal pendulums are always released within 15 degrees of equilibrium. That way there's no damping. It's just an interesting phenomenon that if you have an ideal pendulum, as long as the angle of release is within 15 degrees of equilibrium, you will get no damping and basically it'll swing back and forth forever. Okay? Now, when we talk about the mechanical energy of pendulums, all right? Now, you're going to see more about the mechanical energy of springs in the videos, but let's look at the mechanical energy of a pendulum. There's only two kinds of mechanical energy that a pendulum has. There's translational kinetic energy, because it's got a tangential velocity as it goes back and forth. And, of course, gravitational potential energy. Because it swings in an arc, the bottom point is the lowest, and therefore we would take that to be a height of 0. The amplitudes are above that. So it will have the maximum gravitational potential energy when it's at amplitudes. So the maximum gravitational potential energy is at the amplitudes. Okay, the minimum gravitational potential energy is at equilibrium. On the other hand, you've got your maximum kinetic energy at equilibrium, because that's where it's traveling the fastest, and you have your minimum kinetic energy at amplitude where it stops to change direction. Okay? All right. And momentum must be conserved. So at every point along through here, the two energies must combine to give you the same total energy, whatever that value is. Okay? All right. And that's about it. I will talk to you guys again on Thursday. Bye-bye.